Hello students, so far we have discussed the introduction to computer architecture, that is unit 1. From today we are going to discuss about unit 2, data representation. In the digital world, everything is based on digits. In every method, the calculation is processed on the digits. And most importantly, the computer only understands the binary language, that is digits 0 and 1. These digits are input for the system to fetch, process and execute the instructions. Data is the raw information or collection of instructions provided to the system to execute that instruction to gain a required output. So, it becomes necessary to enter that data in a particular format according to the system's requirement, which is called data formatting. So data format is nothing but the exact way of representing data in binary. It tells how, why and which data format is suitable for executing that particular system's task. Various kinds of data are entered in the system, and data format provides the user criteria to systematically use that data. Now we will discuss about why are data format necessary to understand computer organization and architecture. The answer is, in computer organization and architecture, data formats are necessary to understand in architecture. During designing, the CPU user needs to decide that the CPU will take numbers, that is data, in which format. Some criteria are already set in the system for the working of the processor. For example, if a system understands the numbers 1's complement number representation and provides CPU data in 2's complement number representation, the CPU gives you an incorrect answer. So in a system architecture, the designer already set a word size like a word size of 16-bit or 32-bit or 62-bit. If the user system is 32-bit and the user is installing an application of 64-bit configuration, that application does not work properly. The application always shows a problem in the running of the system. The types of data input in computer are shown here in the flowchart. So a data can be represented in number or character, and the number can be an integer number or a real number, and an integer number can be a signed number or unsigned number. Similarly, a character can be of a floating point representation or fixed point representation. So we can represent a data in number or character, and the number can be of an integer or real number, and the integer number can be a signed or unsigned number. Similarly, a character can be of a floating point representation or fixed point representation. So in this video lecture, we will be discussing about the integer, signed integer and unsigned integer representation, right? So first we will discuss about number. So numbers are digits 0 to 9 used for calculating, that is subtraction, addition, multiplication, division and other mathematical calculations. Mathematics is originated with numbers in a computer system. Numbers are represented in different ways. Ways of number representation are integer, real number. Okay. So first we will go with integers. Integers are the whole numbers. You all know that integers are whole numbers, not a fraction, represented in the computer as a group of binary digits, that is bits. These are some of the data types commonly used in computer. Integer can be positive, negative or 0, like 34, minus 567 or 0 or 4556, like that. Okay. So an integer can be of a signed integer or unsigned integer, as I have told already. Now let us discuss about unsigned type of integer. An unsigned integer can hold a whole number, that is from 0 to n. The number 0 to n can be 0 and positive number like 0 to 36,277. Unsigned integer cannot use negative values or numbers. Keep in mind, that is, unsigned integers cannot use negative values or numbers. If the computer has a 8-bit register to store number, the range of unsigned integer is 0 to 2 to the power n minus 1. The smallest number is equal to 0 and the largest number for a 8-bit number is 2 to the power 8 minus 1, that is equal to 255. Similarly, if the computer has a 16-bit register to store the number, the range of unsigned integer is the smallest number is 0 and the largest number is 2 to the power 16 minus 1, that is 65,535. If a computer is of a 32-bit register, then the largest number is of 4 billions. Okay, so the general formula for n-bit is of 0 to 2 to the power n minus 1. Now we will discuss about signed integers. Like unsigned integers, signed integers also represent 0 for positive value, but it can also represent negative number. It is representing real number as fixed point representation in the system, and we'll discuss further in detail now. In a computer system, there are 3 ways to represent the signed integers, as I have shown here. The signed number can be represented as use the MSB bit as signed bit, or it can make use of 1's complement for representing the signed number, or it can use the 2's complement for representing the signed number. Let us discuss each and everything in detail now. First, we will go with the most significant bit. The leftmost and higher order bit in the binary number have a higher number. For example, in binary number 1001, the MSB is 1, and the binary number 0011, the MSB is 0. If MSB is 0, then the number evaluated is positive. If MSB is 1, then the number evaluated is negative. LSB, least significant bit, is the smallest bit in the binary number series at the rightmost side. For example, in binary number 1010, the LSB is 0, and in binary number 0111, the LSB is 1. The computer only understands binary numbers where 0 is for positive and 1 is for negative. In representation, 1 bit is reserved for the number. Let total number of bit is equal to n. Sign bit is equal to 0. It means number is positive. If sign bit is equal to 1, then it means the number is negative. An important point is, for all positive signed integer numbers, all the 3 ways, sign magnitude, 1's complement, 2's complement, have the same representation. Okay, I have shown an example over here for representation of 25 in 8-bit using signed magnitude representation. Okay, the same I have represented it for minus 25 in signed magnitude representation. So the largest positive number in signed magnitude representation is 2 to the power n minus 1 minus 1, and the largest unsigned integer is 2 to the power n minus 1. In 1's complement for negative number, the working rule for finding 1's complement of negative number is represent the positive binary number of given number. Step 2 is inverse the digits, that is make 0 to 1 and 1 to 0. Hence we get 1's complement of the negative number. I have shown an example over here, representation of minus 45 in 8 bits using 1's complement. You can see it and you can understand it easily. Next is of 2's complement for negative number. The working rule for finding 2's complement of negative number is step 1. Find the binary of positive number. Step 2. Scan that binary number from right to left. When 1 appears first, then write the 1 as it is and inverse rest of the remaining digit as shown in the example shown here. So the general formula for n bits in sign magnitude representation is minus 2 to the power n minus 1 to minus 1 to 2 to the power n minus 1 minus 1, and in 1's complement it is equal to minus 2 n minus 1 minus 1 to 2 to the power n minus 1 to minus 1, and for 2's complement also it is of same. Here I have shown a table. It lists all possible 4-bit signed binary number in the 3 representation, that is signed 2's complement, signed 1's complement and signed magnitude. Okay, you can check it. Here I have shown some examples of signed and unsigned number addition and subtraction. You can see it and you can understand how the addition is being performed using 1's complement as well as in 2's complement. Here this example shows addition of addition of plus 7 with minus 7 using 1's complement. You will be getting an answer of 6. The same being done by means of 2's complement also, right? If we do subtraction in binary arithmetic, subtracting a number a and b is by a minus b, that is a plus 1's complement of b. If we use 1's complement representation, and a minus b is equal to a plus 2's complement of b if we use 2's complement representation. So I have chosen an example for subtracting 5 minus 2 using 1's complement, as well as I have same using 2's complement also, 5 minus 2 using 2's complement. So if you add 2 large positive numbers or 2 large negative numbers, then a overflow occurs. For example, try adding plus 5 and plus 6 in 2's complement magnitude representation. We will be getting minus 7. The answer we got was minus 7. It should be 13, that is 6 plus 7 is of 13, but remember that the range of 2's complement is only from minus 8 to 7. It cannot represent 13 with only 4 digits. Hence, overflow occurs. If you use more binary digits to represent your signed number, the overflow problem can be addressed. So that's all with today's video. We will be seeing the next topic in the next video lecture. Thank you.